So this morning I spoke to you about the Ramanujan conjectures. One of the things that I didn't have time to state was an important theorem in Ramanujan's paper. Ramanujan seems to, so I told you about this product n equals 1 to infinity, 1 minus q to the n to the power 24. This Dirichlet series, this power series. And in that paper, in the same paper of 1916, Ramanujan associates the Dirichlet series this Dirichlet series, and he says that his second conjecture about the first and second conjectures, the multiplicativity of the tau function combined with that recursion relation, allows him to write this as an Euler product. I'll just write it in this fashion so that it's clear. Euler product. For those of you who were at my talk last week, where I was trying to give you an informal introduction to the Langlands program, I told you that the Riemann zeta function is the prototype of zeta functions, but that's a one-dimensional object, and somehow Ramanujan stumbled on a two-dimensional object. That's the idea. That's the significance of this calculation. He makes this statement. Of course, this follows if you had the first and second conjectures, and he also seems to be aware that L delta S extends to an entire function, and satisfies a functional equation. Functional equation relating S into, I believe, 12 minus S. So the line of symmetry here is the line real part S equals 6. And somehow, as I said, this is an important episode in the history of mathematics because this is a two-dimensional L function as opposed to a one-dimensional one, which is the classical Riemann zeta function case. And so this is essentially the starting point of L functions or L functions attached to modular forms. And that is the beginning of the Langlands program that I was talking to you about last time. All right, so that comes out very neatly, and perhaps either, well, if I don't know how much you have time for, but I think later on we will come to the L series attached to modular forms and derive those functional equations. So you don't have to worry about if you don't understand all of that stuff right now. So let's discuss now that I've crammed into you the level 1 theory. I want to discuss the higher level theory now. And so recall a congruent subgroup gamma is a subgroup that is a subgroup containing gamma of n for some n. And the minimal n for which this is the case is called the level of gamma. So let's take a congruent subgroup of level n, and we will discuss modular forms with respect to that particular subgroup. So let gamma be a congruent subgroup of level n. we want to discuss, we will study holomorphic functions on the extended upper half plane, holomorphic functions on the extended upper half plane satisfying f of az plus b over cz plus d equals cz plus d to the power k f of z for all a, b, c, d in gamma. Now recall that the extended upper half plane is the usual upper half plane along with these cusps. In the level 1 case, the full modular group case, all the cusps were equivalent to the point at infinity, and so there was no detailed discussion except the Fourier expansions at infinity. Now I need to discuss Fourier expansions at cusps, and what I mean by all that stuff. What does it mean for something to be holomorphic at those cusps? Because holomorphic in the upper half plane, that's pretty clear. That's the classical notion. But what does it mean? What does it mean for f to be holomorphic at a cusp? That's the question that I'd like to address. So recall that these fundamental neighborhoods of the point at infinity, recall that these sets U sub c, collections of complex numbers in the upper half plane whose imaginary part is bigger than c. These are fundamental neighborhoods of I infinity. And we have the mapping that takes z into e to the 2 pi I z, which is q, the variable q, so that by making this change of variable, the discussion of holomorphicity at infinity was translated to holomorphicity at 0. And that you're familiar with that map, so it's a power series in Q, and then we could talk about it that way. That's how we did it in the level 1 case. Here, we do something similar, but we have to be a bit careful about these inequivalent cusps. So the part of the problem is the following. Now, there may be several difficulties. For one thing, it may be that the element 1101 is no longer in our group. Before 1101 was in the group, and that translated as f of z plus 1 equals f of z, and that, of course, when you move to the Q series, it translates as a Fourier expansion, which is periodic with period 1. But now it may not be that case, but rather 1n01 is in gamma, because gamma has level n. So we're taking gamma of level n. So that means gamma contains gamma of n, and this is an element in gamma of n. Therefore, this element is there, and therefore this translates the modularity condition. That condition that I wrote there translates as f of z plus n is f of z for all z in the upper half plane. So the periodicity is now period n, so it makes sense to perhaps parameterize not with q equals e to the 2 pi I z, but rather e to the 2 pi I z over n. this may be the variable for discussion. In fact, what we do is we take the least h, we take the least value of h, least positive h, such that 1h01 lies in gamma. And then, of course, f of z plus h is equal to f of z, and therefore it makes sense to parameterize or look at the mapping z goes to this change of variable q equals either 2 pi I z over h. This may be the more appropriate thing for discussion of behavior firstly at infinity. Now, this is almost good. One can actually show here that h will divide the level. Such an h will always divide the level, and we consider therefore the Laurent expansion. We may consider the Laurent expansion around q equals 0 under this change of variable. And that's, so in such a case, we can write our f of z as, because it's a holomorphic function, we'll start a n equals 0, and a n equals 0, a n q to the n, where q is equal to either 2 pi I z over h. And we'll call this the Fourier series of f at infinity. Okay, so that makes a little bit of sense. So that's not terribly surprising. Now, what about these? So I've told you what it means for a function now to be holomorphic at infinity with respect to this group gamma. Now I have to talk about the holomorphy at all these other cusps. Well, before I do that, note, so observe that if RSTU is an element in SL2Z, let's call this gamma, then F slash gamma is again holomorphic in the upper half plane. And if F is a modular form on gamma, then F slash gamma is a modular form on the conjugate subgroup gamma. So if gamma was a congruent subgroup, that is capital gamma contains gamma of n, and gamma of n, capital gamma of n, is a normal subgroup. Therefore, any conjugate is also a congruent subgroup. So this certainly makes sense. It's a congruent subgroup again. And we see that F slash gamma is again H periodic. If F was H periodic, F slash gamma is also H periodic. So we can talk about the shifted function. So now I can, with this definition, with this understanding, what do I mean if x is a rational number, is a cusp? We take gamma such in SL2Z such that such that gamma sends x to infinity. So we know that all the cusps, the rational numbers, are equivalent under SL2Z. So we take an SL2Z transformation that sends x to infinity, and then consider to say that f is holomorphic at x is equivalent to saying that f slash gamma is holomorphic. So I take x to infinity. So x equals gamma inverse of I infinity. So to say that f is holomorphic at x is equivalent to saying f slash gamma inverse is holomorphic at infinity. So that's the definition that we will adopt for holomorphy at the cusps. So you take the, so I told you what it means for it to be holomorphic at infinity with respect to this Q expansion, Q being e to the 2 pi I z over h, and then we take a SL2Z transformation that takes the rational cusp to infinity, and then do this little trick, because we already discussed what it means to be holomorphic at infinity. We're actually talking about this guy being holomorphic at infinity. That's what we mean by being holomorphic at x. Okay, so that takes care of the discussion here. And now when we talk about the Fourier expansion of f at the cusp x, this means the Fourier expansion of f slash gamma inverse at infinity. So when I talk about the Fourier expansion of a holomorphic modular form at a certain cusp x, it means that we're talking about the Fourier expansion at, did you have a question? Oh, okay. At infinity. Okay, so that takes care of that part of the definition. Now, I've made a bit of a oversimplification. There's a small snag, but I'm not going to belabor this point. There's a small snag, remark, technical snag. Whatever I said is fine. There's only one small problem, and this has to do with the fact that that minus the identity may not be in gamma. Technical snag: if minus the identity element is not in gamma, that could happen. And if that's the case, then the point is that minus 1 h prime 0 minus 1, so there could exist an h prime which is smaller than h, such that this is in gamma inverse capital gamma gamma. So remember, I told you we take our small h such that 1h01 is in that group, but if it happens, there could be a smaller h prime such that minus 1 h prime 0 minus 1 is in my group. And if you look at the modularity relation, that means that f of z plus h prime is equal to f of z. So there's a periodicity which is smaller. It's not the full period, right? So this can happen, and therefore the Q expansion may not be, it should not be with respect to e to the 2 pi I z over h, but rather e to the 2 pi I z over h prime. And however, the square of minus 1 h prime is in gamma. So if it happens, is in gamma inverse gamma, it could happen that this is in here, and the square of it then will be here. And this is now more like the discussion I just finished doing. And so the question of whether it's 2h or h is a moot point, and it has to do with whether or not this element is in the group or not. So for the time being, let's just assume that this element is in our group. so we don't need to really worry about it. And then we can define what's called the width of the cusp. Width of the cusp is this value of h. Is this value of h prime or 2h prime, depending on. So it'll always be either h prime or 2h prime. So here's the recipe. So I have a cusp x. I find a gamma such that gamma x goes to infinity, and then look at the smallest h prime such that either this happens or 1h, whatever it might be. If it happens that there is this situation, then that'll be the width of the cusp. If it happens that you're not in this situation at all, you can just happily move in this way, and then that'll be the width of the cusp. So it's a small issue which I will not belabor. And if there are these half-integer orders of cusps, those are what are called irregular cusps. So this is just a technical snag that one should consider perhaps, but not on the first round. But I'll put that in for now. So, given our Q expansion, at x, at the cusp x, we can speak of the order of f at x, and that'll be denoted v sub x of f. It's the smallest n such that the Fourier coefficient an is not 0. So we talk about the the Q expansion at the cusp. This is what I discussed here. We look at the Q expansion of the cusp, and the smallest n for which an is not 0 is the order of the 0 at that cusp. A small exercise in order to understand. Suppose that gamma and tau are in SL2Z such that gamma of I infinity and tau I infinity, so these are both cusps, are now gamma equivalent. Then the order of the function f at the cusp gamma of I infinity is the same as the order of f at tau infinity. So in other words, the order of the function f at the cusp x depends only on the equivalence class of the cusp. See, the cusps are gamma is acting on it, right? So there will be equivalence classes of cusps. So thus, the order of f at a cusp depends only on the gamma equivalence class that it belongs to. Okay, so with these technical issues out of the way, now I can state a few theorems. So given a congruent subgroup gamma of SL2Z, we define the space Mk of gamma and Sk of gamma to be the vector space, to be the C vector spaces of modular forms of weight k for gamma, which are, of course, these are holomorphic modular forms at all the cusps, and in the case of Sk of gamma, holomorphic at all the cusps. So let me just put this in brackets. Holomorphic at all the cusps, and for the Sk vanishing at all the cusps. So these are the vector spaces, and we would like to study these vector spaces just like we studied the level 1 case, the full modular group case. So in that case, you will remember that we essentially constructed the Eisenstein series with our bare hands. We explicit constructions of modular forms with our bare hands. So we're going to do the same thing here. So Eisenstein series. So let k be bigger than or equal to 3, and n your level of gamma. Let g be an element in z mod nz squared. Define g sub k comma g of z to be this double series where m and n, the mn is congruent to g modulo capital N. And of course, as before, the dash on the sum means mn is not equal to 0, 0. So simultaneously they can't be both 0, but this is not surprising. These are essentially similar to the objects that were introduced earlier.
I think belonging to like all the equivalence classes.
Yeah, that's the point. In the case of SL2Z, all the cusps are equivalent to infinity. So there was no need to discuss other cusps. It suffices to discuss infinity. Here, we need to discuss there might be some of the cusps might be equivalent to infinity, but some of them may not. So we really need to discuss equivalence classes of cusps.
Sure, but like you've defined here for each x rational.
Yeah.
So first of all, is it true that
No. What will happen is it happens to be with respect to, see, it depends on this this transformation, the gamma, okay? The transformation gamma lands you in a different group. So that the point is that when I have a rational number x and a gamma such that sends x to infinity, the point is that this guy lives in is a modular form in mk of gamma inverse, something like that. So it will be a conjugate. It'll be in a different group. So we're really talking about Fourier expansions of different forms in different groups. That's what it really means. So now I have to make sense of the Fourier expansion at the equivalence class of Cusp. So here, I need to tell you that this is actually well defined. The order of the point is well defined. This is a little small exercise that you have to do. So then I can discuss happily the orders of the thing. But the Fourier expansions will be different depending on your gamma that you're going to use. Yeah. All right. So this is looking pretty much like before, except I've got these congruence conditions. So I have the condition that m and n have to be in the residue class specified by this little g. All right, so once we have that, it's a small matter to check then. If you take gk little g and slash it with gamma, where gamma is in SL2Z, then it turns out that this is equal to G sub k G gamma. So what do I mean by G gamma? Well, G gamma, G is a an element here. So when you take an element, let's call it Mn, and you have a matrix A, B, C, D, then this is what? Am plus Nc, Bm plus Nd, right? This is the I should have made it a row vector, sorry. Oops. How did that happen? Okay, Am plus Nc plus Bm plus Nd. So you have a vector like this. So this is what I mean by G gamma. So you're going to get another two-tuple of residue classes. So when I'm looking at modular forms, summing over all the m's and n's in a certain residue class, and I hit it with gamma, you get this property. So that's not difficult to check. And in particular, if gamma is in gamma of n, then and G equals G0, G1, we see that G0, G1 are NS and T U is going to be equal to R G0 plus N G1 T and NS0 plus G1U. Right? In other words, it'll just simply be R, these diagonal components. So you're just modulo n. So modulo n, this is just R G0, G1U. So that means you're just multiplying it by the diagonal entries modulo n. So because I have an element in gamma of n, then these two diagonal entries are congruent to 1 mod n. Therefore, in that case, we see that G0, G1, when you hit it with this matrix gamma, that is congruent to G0, G1. In other words, this guy is a modular form of weight k for gamma of n. Okay, so that gives you, of course, I didn't discuss the holomorphy at the cusps, but let's not worry about that right now. But it certainly transforms, because G gamma is the same as G, it turns out that these are modular forms of weight k for the group gamma of n. Now there are some standard functorial ways of taking things from downstairs and moving them upstairs. So here's a small exercise. If gamma is a congruent subgroup of level n, and and gamma 1 to gamma r are coset representatives, for gamma of n in gamma, then F equals J equals 1 to R G sub K G gamma J is a modular form of weight k in gamma. So here, just as we constructed with our bare hands modular forms of weight k in the level 1 case, here we're constructing modular forms of weight k for gamma of n by that comment. And then now that I've constructed some modular forms for gamma of n, I'm telling you how to construct them for any arbitrary subgroup gamma by this little coset trick. And it's a small exercise to check that this is actually. So this is a non-empty theory. I mean, we have to have examples, right, before you build a theory. So this gives you lots and lots of ways of constructing examples of explicit modular forms. I mean, there's a general theory of Poincare series which gives all explicit constructions of modular forms using these kind of tricks, but I will not discuss Poincare series in these set of lectures. Okay, so these are, of course, modular forms, all right. They satisfy the transformation property, but I didn't discuss the behavior of the cusps. So for that, you need to come up with its behavior, its Fourier expansions. So here we will discuss the Fourier expansions of higher level, the Fourier expansions. Of higher level Eisenstein series. So let G be equal to A1, A2. And write GK G of Z as BK G of 0 plus So I'm trying to write down the Fourier expansion for these Eisenstein series. And so what are these coefficients? Well, BKG of 0 turns out to be 0 if A1 is not 0 mod n. And it turns out to be what's called the Hurwitz zeta function, special value of the Hurwitz zeta function. A1 is 0 mod n. And BKG of n in the general coefficient here is given by minus 2 pi I to the power k over k minus 1 factorial n to the k summation d divides n d to the power k minus 1 sine of d e to the 2 pi I a2d by n, where d divides n runs over all divisors, both positive and negative, and n over d has to be congruent to a1 modulo n. So here I'm running over both positive and negative divisors of n. So if it's a negative divisor, sign will be minus 1. If it's a positive divisor, it will be plus 1. And so before, things were rather simple because we were just looking at k minus 1th powers of the divisors of n. But now we have this extra complicated factor that intervenes. This term, 2 pi I to the k over k minus 1 factorial, looks similar because we had that in the earlier case as well. The proof of this fact is very much like before, and I'll just give an outline instead of going into the nitty-gritty details, but it's, as you suspect, it's the same thing as before. You just have to set it up in such a way that you use Lipshitz's formula, and then once you plug that back in and do the obvious manipulation, you end up getting this, okay? Proof. So computing the constant term is routine. So essentially, what do I have to do? I have to check here if m is 0. Sorry, if a1 is 0, where did I write it? Here it is. A1 is 0 mod n, then you know you're going to pick it up. If a1 is not 0, you're not going to pick up that. You're not going to pick up any term, and so there will be this thing which will not be 0, and so at z equals I infinity, this whole thing is 0. So the only time it might survive is when that thing is 0, and so I'll leave this this calculation to you to do. So if so we can write we can write it like that. The inside sum here, n, can be rewritten as n times j plus a2. And so this sum here can be rewritten as a summation over j of and you recognize this, so by moving the n to the k outside, you can see that this can be rewritten as n to the minus k times summation j going from minus infinity to infinity of j plus mz plus a2 divided by capital N to the power k. So remember, the Lipschitz formula was 1 over j plus some z to the power k, so you now know how to do this and write down its Fourier expansion. So you take that Fourier expansion and shove it back in here, and then collect terms. So I'll get you started, and now you can try to finish that, and then when you collect terms, exactly as we did in the classical level 1 case, when you collect terms, you're going to get this. So this is where the 2 pi I to the k over k minus 1 factorial comes in. If you remember the Lipschitz formula, it gives you the Q expansion, that's the constant term. All right. So a special role will be played by these Eisenstein series. So let me kind of introduce this to you. Let's do an example. Let e to n of z be the Eisenstein series E2 introduced this morning minus n times E2 of nz. So remember that E2 is not a modular form, but what's called a quasi-modular form. But we did determine the modular transformation relation for E2 of z. The question is that where does this live? Well, this is a modular form, surprisingly, in gamma naught of n. So let's see how this is done. So I have to check firstly, the holomorphy at the cusps are taken care of. you have to check a little bit about that. We already checked the behavior at infinity. We'll have to check that it actually behaves properly at the cusp, but it does, because we had that Q expansion that we gave this morning. So now, this is equal to E2 of AZ plus B over CZ plus D. The first term here is CZ plus D squared times E2 of Z plus this fudge factor right from the transformation rule for E2 of AZ plus B over CZ plus D. This is it. This is what you have. So I have to do the same thing here as well, plus or minus. Well, let me just leave it like this for now. And here I'm going to change variables. Yeah, that's. Oh, sorry, there should have been n, right? There's an n here. That's why. Okay, that makes sense. Okay, n CZ plus D. I was wondering how that crept in. It's n times z, right? So I change z to AZ plus B over CZ plus D. I have to multiply by n. So this is what you have. Now let's look at the last term. The last term, I'm going to write it as A of nz plus bn or C over n nz plus d. Okay. That's the last term, the last expression at E2. So this guy is the modular transformation applied to nz. A times nz plus b over c over and the matrix. So C, the point is that the matrix I have is in gamma naught of n. A, B, C, D is now in gamma naught of n. So what does that mean? It means that C is divisible by capital N. Okay? So therefore, I can look at this matrix as A, B, C over N, D. This is a matrix, sorry, Bn. There. Okay? So this is a matrix AD minus BC, which is still 1. It's an SL2Z. Okay, so I know this morning how the E2 transforms under SL2Z, right? So here's my matrix, and it has to transform as C over N. So it'll be transforming as CZ plus D squared, the E2 of NZ plus 6 times C over N CZ plus D over pi r. See, keeping in mind that Z is replaced by NZ and C is replaced by C over N. See, that's why okay, so keeping that all in mind, you get this. So this guy here, so it's a little messy. I'm sorry I messed it up here, but let's just check what happened. So therefore, E2 N of AZ plus B over CZ plus D equals minus n times minus 6 C 6 C over n, and the n cancels, so that's 6c, cz plus d over pi I. So the point is that these guys disappear, these fudge factors disappear, and you end up getting that this is equal to cz plus d squared times E2 of z. So you end up getting this. Therefore, E2n is a legitimate modular form of weight 2 on gamma naught of n. Okay. The other interesting thing is that we know the Q expansion or the Fourier expansion of E2n. Note E2n of z is equal to, well, it's equal to E2z, which is what? 1 minus 24 summation n going from 1 to infinity of sigma 1 of n q to the n, where now keep in mind that q is equal to either 2, this was either 2 pi I z here, okay? 2 pi I z here. So I have to, when I change this n, so minus n times summation minus n sigma 1 n q to the n. N. So this is your Q expansion that goes with it. So the constant term is 1 minus n, and then you have these other expansions. So the Fourier coefficients are going to be either sigma 1 of n or sigma 1. It depends on the it'll be sigma 1 of n in general, except when the n is divisible by capital N, in which case you have to subtract some fudge factor. All right. So last time we kind of used our Eisenstein series to describe the space of modular forms of weight k as a polynomial ring in E4 and E6. We did that rather easily. Trying to do the similar thing in the higher level case is not so easy, and in fact doesn't work so cleanly. One actually has to use Riemann surface theory to do a clean job of the description of these Eisenstein series. So this is a little bit beyond the scope of these lectures. So in general, to derive the valence formula for f in mk of gamma, as well as the dimension formulas, for these spaces, one needs to use complex function theory, and in particular the Riemann-Roch theorem. So this would be a good thing, perhaps some of you can do as a seminar afterwards, complex function theory, do Riemann-Roch theorem and try to understand it and see how it applies to get some of these formulas. A good reference for both of these things is either Shimura's classical book or the Diamond-Sherman book. both of these books give you the nitty-gritty details of this derivation. So what I'm going to do is I'm just going to state the results in general, the valence formula and the dimension formulas. So first, before we do that, let me talk about elliptic points. So a point in the upper half plane is called an elliptic point if the stabilizer of Z with respect to gamma, that is, the collection of elements that fix Z, and the elements are sitting in gamma. So I'm doing the general case now. The stabilizer of Z in gamma is strictly larger than the trivial plus or minus the identity. So plus or minus the identity both act trivially on Z, so they stabilize Z, but if the stabilizer of Z in gamma is strictly larger, we say Z is an elliptic point. There, What, the stabilizer? Yeah, sorry. Yeah, we have to, that's right. Elliptic. If gamma Z is strictly larger than and of finite order, yes. No, well, he's talking about, for example, take the extended upper half plane, the point of infinity. The point of infinity, the stabilizer of infinity are those matrices 1 and 0, 1, right? So there, the group is infinite. So it could, but that wouldn't be called an elliptic point.
Other than the Cusp?
Yeah, generally these are finite, yeah.
This is not so it is not a Cusp, so it will be finite.
In that case, if it's not a cusp, it's finite. You're right. Yeah. So let's just to be on the safe side, we'll just leave it like that for now. But you're right. Okay, so these are elliptic points, and we have to take them into consideration before writing down the valence formula. So the order of the elliptic point is the size of, see this, we have to keep on putting this down. So in the case, in SL2C, in case gamma is the full modular group, I, rho, and rho squared are the only elliptic points in the fundamental domain. In the fundamental domain. And some remark, exercise or remark. If gamma has finite index, there are only finitely many elliptic points. And so now the valence formula is the following theorem. So let gamma be a congruent subgroup F in MK of gamma. f not identically 0, then summation. So we're looking at the upper half plane, and we're modding out by the action of gamma, and I'm using this notation for the fundamental domain. Okay, now I'm going to use this notation for the fundamental. So we're now going over points in that. Vz of f is the order of the function at that point, and now modulo this order of the stabilizer. This is equal to k over 2 times epsilon 2 over 2 plus 2 epsilon 3 over 3 plus epsilon infinity plus 2g minus 2, where G is the genus of, okay, so this is, so I've added the cusps as a compact Riemann surface. Compact Riemann surfaces are homeomorphic to a sphere with G handles, okay? So in the case of the SL2Z, we just had a sphere because we just added that point at infinity. The genus was 0 in that case. So in general, it may not be 0, it'll be higher, and so that's what we mean by the genus of a Riemann surface. Every Riemann surface, every compact Riemann surface is homeomorphic to a sphere with G handles, and that G is a well-defined number. So that makes sense. So what is epsilon 2 and epsilon 3 and epsilon infinity? So first, let me point out that this is over these inequivalent points. And epsilon 2 is the number of elliptic points of order 2. Epsilon 3 is the number of elliptic points of order 3. These are the only two finite orders actually that can occur, 2 and 3. And then epsilon infinity is the number of inequivalent cusps. So that's the valence formula, and you can't. Well, I think it's not easy to derive in that naive fashion of contour integration that we do. I think you have to use Riemann rock in a non-trivial sort of way. Oh, yeah. The dimension of the vector space MK gamma is also equally similar. Gamma congruent subgroup. K is even, and the dimension of MK gamma is equal to K minus 1 G minus 1 plus K over 4 epsilon 2 plus K over 3 epsilon 3 plus K over 2 epsilon infinity, if K is at least 2. And if it's 1 if K is 0. And the dimension of the space of cusp forms is given by this minus epsilon infinity. That is the number of inequivalent cusps. In other words, there's a way to actually construct Eisenstein series, linear combinations of Eisenstein series which vanish only at one cusp vanish at all the cusps except for one. And so you can construct a basis of the number of, so you remove those, and then it turns out that that's the dimension for the space of cusp forms. Okay, I'm quickly running out of time. So what I will do now is essentially what I did in the book, that sometimes if you, because of the fact that these formulas are being derived by using complex function theory and the Riemann-Roch theorem, I supply another way of getting some bounds which are equally useful, not precise formulas, but bounds for the space of dimension of these spaces. And this is using what's called Sturm's bound. So if you don't want to use the Riemann-Roch theorem to derive these formulas, one can derive weaker results without Riemann-Roch. And I supply here what's called a Sturm's bound. So gamma is a congruent subgroup. F is a modular form of weight k for gamma. R1, R2 to RT are the inequivalent cusps. Then if, so one can actually show this, if the order of the form at each of these cusps adds up, if all these orders add up to something bigger than k over 12 times the index of gamma, see, the point is, if minus I is in gamma, then this is the same as gamma. If minus I is not in gamma, it just increases the index by, cuts it down, increases by 2. So, or cuts it down by 2. So that's all you have to keep on remembering. If this condition holds, then F is identically 0. So you can't have too high orders for the function at these cusps. So this is actually very simple to prove. I do that in the book, and if you have time, you can try to go through that proof. But it's sufficient to have it for a variety of applications. One of the nice applications is, if you want to establish certain, so you have a candidate, and you'd like to say that the one modular form is the same as another modular form. You already have two candidates and you suspect that they're the same, and you start calculating the Fourier coefficients, and let's say the first million turn out to be the same. Can you conclude that they're the same? So that's the kind of computational application one of that you could use for this kind of thing. So here's a kind of a corollary application. If F and G are modular forms of weight k on gamma, and the Fourier coefficients, the Fourier coefficient of F coincides with the Fourier coefficient of G for all n less than or equal to this number, star, let's say, then F equals G. So that's a kind of a very good thing to have. There's an analog of this for congruences. If I have an of f and an of g, they're ordinary integers, and I've established a congruence between the mod p for some prime p up to a certain point, can I assert that they're congruent? And that I worked out in one of my papers, a mod p generalization of Sturm's bound. All right, so you can study that. And this particular thing allows us to write down another bound for the dimensional space, you can get that the dimension of mk of gamma is always less than or equal to 1 plus this star, this quantity. So it works for various purposes. And in particular, I think the results using Sturm's bound and these inequalities are sufficiently strong to deduce that M2 of gamma naught of 2 is a one-dimensional space spanned by E22. So remember what E22 was. E22 of Z is equal to E2 of Z minus 2 times E2 of 2Z. So this guy generates the space of modular forms of weight 2. So this is like your fundamental thing. And it turns out you can use, again, these Sturm bounds to do the following calculation, that E22, so the dimension, so M2 of gamma naught 4 is a two-dimensional vector space generated by E22 and E24. So you can get these kind of small dimensional results where explicitly you're constructing bases for your space of modular forms. Like the neat, very clean expression that we had for level 1, unfortunately is not so clean and neat as you go up to higher levels, but at least in these baby toy cases of gamma naught 2 and gamma naught 4, you have these very clean results. The reason I write this on the blackboard is because I'd like to tie some of this to my first lecture on Q series and writing sums of 4 squares that we were trying to, the Jacobi formula that we had. This morning we met the Dedekind eta function. We met the Dedekind eta function. And in a way, we also met the theta function in the very first lecture. Q is equal to 2 pi I. And using the Jacobi triple product identity, it's not difficult to see, and we already saw it actually, you just have to review your notes, that this is equal to equal to this. So you go back, look at your first lecture, and you will see products of 1 minus q to the n's floating around. And when you change your variables and put q equals e to the 2 pi z, you'll find that this is actually what you proved. You've written your theta function in as a product of or a quotient of eta functions. Okay. Now you will remember that the eta function satisfies the functional equation that I wrote down in the morning, and so when you work it out, it's not difficult to show that theta of z over 4z plus 1 turns out to be equal to 4z plus 1 square root and we also have theta of z plus 1 equals theta of z. Now this corresponds to the matrix 1, 0, 4, 1, which is an element in gamma naught 4. And of course 1, 1, 0, 1 is also an element in gamma naught 4. And the group generated by these two elements is gamma naught 4. Okay, so exercise. gamma naught 4 is generated by 1041 and 11101. Therefore, we have that if I take the fourth power of the theta function, that'll be 4z plus 1 squared theta of z. And therefore, this implies that the fourth power of the theta function, this one, is an element of weight 2 on gamma naught 4. All right, so now with this nice little calculation, I've worked it in the book so that you don't really need the Riemann-Roch theorem to get the dimension of the space. You can actually do it with your bare hands and the Sturm bound, and I actually do that calculation in the book. So these are two linearly independent spaces, and from Sturm's bound, the dimension is bounded by 2, so it is actually equal to 2. And these are the basis elements. And therefore, since theta to the 4 lives in the space of modular forms of weight 2 on gamma naught 4, we must be able to write theta 4 as a linear combination alpha E22 plus beta E24. And when you work it out, so here you work out a few small coefficients of the Q expansion, the first 2 or 3, and then you have two unknowns, alpha and beta. You get a system of two equations in two unknowns, and you solve for it, and lo and behold, it turns out that theta to the power 4 is equal to minus 1/3 E24. And when you go back to the Q expansion of E24, when you go back to the Q expansion of E24 and you compare coefficients, so the left-hand side here is giving the number of ways of writing n as a sum of 4 squares, and the right-hand side is an expression involving the divisor function, and lo and behold, it coincides with Jacobi's formula. So the point is that I've tried to make either by this morning's lecture and the lecture now is that, you know, mathematics proceeds usually by experimentation and conjecture. So it's an amazing thing that some mathematicians have remarkable insight, like Ramanujan had remarkable insight had a good nose for what's important and what's interesting. So he made those conjectures, but it's the tip of the iceberg, you know, there's a bigger theory that you haven't seen, and to come up with the appropriate theoretical basis by which all of this makes sense is essentially what mathematics is all about. So with the observations made by Ramanujan on one hand and made by Jacobi with his formulas for the number of ways of writing n as a sum of 4 squares, and then Ramanujan's own observations that somehow writing a number as a sum of 24 squares is an equally important problem, although we might not be concerned about it in our daily life. It's an equally important problem, and lo and behold, the tau function appears as an error term in these explicit formulas. So that's basically where, and it's all because of the dimensions of the space of modular forms and having an explicit basis for this thing, and therefore writing these formulas for powers of, so you can see that if this is a modular form of weight 4 living on gamma naught of 4, by taking this to the 24th power, we would be concerned with the number of ways of writing n as a sum of 24 squares, but that then belongs to the space of modular forms of weight 12, and we already have a basis for that you can construct for the, you know, using these things, and therefore it's not surprising now that the tau function appears in that expression that Ramanujan had. But Ramanujan didn't have a theory in mind when he made these conjectures. He just observed them by brute force, by not being averse to making these calculations. So that more or less summarizes the theory of modular forms of higher level. So tomorrow we have a break and you'll have 2 tutorials, and the day after I think we'll move on to the theory of the Peterson inner product. Okay, voila, that's it.